Mars in popular cinema is a red stage where everything that can go wrong usually does. Colonies explode, domes crack, crews mutiny, and mysterious microbes turn triumph into disaster. These stories are gripping, but they quietly teach audiences that a permanent human presence on Mars is probably doomed. Real mission planners see a very different picture, built on checklists, simulations, and decades of incremental learning. The contrast between cinematic failure and real-world strategy reveals how survival in deep space actually works. Movies usually begin with a finished colony dropped onto the Martian surface, like a prefabricated city. The first habitat is often enormous, glassy, and fragile because sleek designs look good on screen. In reality, no serious plan starts with a city or even a large town. NASA's reference architectures envision a small crew and a modest habitat delivered over several launch windows. Cargo ships arrive first, robots assemble or prepare infrastructure, and only then do people follow. Films routinely ignore this cargo-first strategy because months of robotic setup seem less dramatic than a ribbon-cutting ceremony on Sol 1. In science fiction, a single failure can wipe out the entire settlement in minutes. A lone airlock sticks, a storm shatters solar panels, or an angry crewmate sabotages life support, and the colony collapses. Actual engineering treats single-point failure as an unacceptable risk wherever possible. Life support systems are designed with redundancy, spare parts, and independent backups, even if that makes them bulkier and less cinematic. Space habitats are tested in analog environments such as Antarctic stations, underwater labs, and desert isolation modules to find obscure ways they might fail. Lessons from the International Space Station also feed directly into Mars planning, because every leak, clog, and short circuit in orbit teaches how to survive farther away. Mars movies often dramatize the planet's weather as if it were a hurricane waiting to happen. Towering dust storms smash habitats and flip rockets, as though the thin Martian air carried the force of an Earth tornado. Real atmospheric data from landers and orbiters tells a calmer story. Martian dust storms can cover the whole planet and block sunlight, but the air is so tenuous that wind pressure is gentle compared with earthly gusts. The main danger is not buildings being knocked over, but solar panels being darkened and fine dust-infiltrating mechanisms. Engineers respond by sizing power systems for long, low sunlight periods, and by exploring dust-tolerant designs like vertical arrays, electrostatic cleaners, and nuclear power. Some mission concepts even plan habitats partially buried in regolith, not to withstand imaginary windstorms, but to shield against radiation and micrometeoroids. Radiation is another area where on-screen drama and off-screen analysis diverge. Characters in films are often either instantly fried by a solar flare or completely ignore radiation altogether. Spacecraft designers, by contrast, treat radiation as a constant low-level hazard to be managed over many years. Data from the Curiosity rover and orbiting instruments has mapped typical radiation doses on the Martian surface and during transit. These measurements guide choices about habitat wall thickness, water storage placement, and where to store food and equipment that can double as shielding. Some concepts use Mars soil piled over living spaces, turning the landscape itself into a protective blanket. Time is compressed in movies because a 2-hour story cannot follow a 20-year campaign. A new colony is declared, the crew arrives, catastrophe strikes, and the project is judged a failure, all in a single fictional mission. Real exploration builds in pauses, rehearsals, and stepwise risk increases. Before anyone sets foot on Mars, astronauts are returning to the Moon under the Artemis program to practice operating far from Earth with delayed communication. Long-duration stays on a lunar surface base will teach how to maintain closed-loop life support, manage dust, and repair critical systems without rapid resupply. Deep space habitats in cislunar orbit and on the ground will serve as testbeds for Mars transit living quarters. Each stage is designed to reveal new problems before the next, more distant step is attempted. Sci-fi scripts often rely on a lone genius who fixes everything with duct tape and a clever idea at the last possible moment. This myth is entertaining but misleading for aspiring explorers. In reality, survival on Mars depends on thousands of quiet decisions made years before launch by multidisciplinary teams, systems engineers, planetary scientists, medics, psychologists, and logistics experts all contribute constraints and solutions that limit how much can go wrong later. Astronauts train not as action heroes, but as methodical operators who follow procedures and report anomalies. Success is measured less in daring improvisation than in how rarely emergencies appear in the first place. Terraforming is another frequent cinematic shortcut that distorts the real timeline of Mars settlement. Films sometimes show cosmonauts pressing a button that triggers rapid atmospheric changes, melting ice caps and turning deserts into forests within a generation. Current science offers no plausible path to transform Mars on that timescale with foreseeable technology. The planet has too little atmosphere, too weak a magnetic field, and too much of its ancient water locked as ice or lost to space. Instead, serious proposals focus on creating small pockets of Earth-like conditions inside habitats and greenhouses. Local environments can be made comfortable long before planetary scale changes are even theoretically viable. Another difference lies in how movies handle the human mind. Many plots hinge on crew members descending rapidly into paranoia or violence as soon as isolation sets in. Psychological stress will indeed be a major challenge, but it is addressed through careful selection, training, and ongoing support. Space agencies study Antarctic winter crews, submarine teams, and isolation experiments like high seas and NEC to understand group dynamics in confined spaces. Tools such as regular communication with Earth, meaningful work, private space, exercise, and conflict resolution protocols are part of the mission design, not afterthoughts. Misbehavior on Mars is more likely to be managed with policies and leadership than to spiral instantly into chaos. Real Mars strategies also rely heavily on using local resources, a topic movies sometimes mention, but seldom explore deeply. The Perseverance rover's MOXIE experiment has already demonstrated that oxygen can be pulled from Martian carbon dioxide. Future systems could scale this process to produce breathable air and oxidizer for rocket fuel. Radar mapping and lander data reveal buried ice deposits that could supply water for drinking, agriculture, and additional fuel production. By reducing the mass that must be launched from Earth, in situ resource utilization makes Mars missions more resilient and economically feasible. Private companies play a major role in many realistic scenarios, even though films usually feature a single monolithic agency. SpaceX, for example, is testing the Starship system with the stated goal of enabling large-scale transport to Mars. NASA increasingly partners with commercial launch providers, cargo services, and technology firms to distribute cost and innovation. This ecosystem approach contrasts with the isolated, top-down organizations often portrayed on screen. Planetary protection is another real constraint often absent from fictional stories of Mars colonization. International guidelines require that missions avoid contaminating Mars with Earth microbes that could compromise the search for native life. Future human missions will need strict biocontainment procedures, careful site selection, and possibly zones where biological experiments are restricted. These limitations make the narrative of reckless exploitation less likely than in adventure films about careless colonizers. Taken together, the real-world practices of redundancy, gradual expansion, psychological preparation, and ethical oversight give Mars settlement a sturdier foundation than cinema suggests. None of this eliminates risk, and early missions will still be dangerous and fragile compared with life on Earth. Yet the trend in spaceflight has been steadily toward higher reliability. From the early days of Apollo to the routine operations of the International Space Station. For aspiring Mars explorers, the lesson is that success will look more like meticulous project management, than like a disaster movie. Skills in systems thinking, teamwork, maintenance, and adaptation to boredom may matter more than dramatic courage. The gap between how Mars fails in movies and how it is planned in reality is ultimately a gap between storytelling and engineering. Bridging that gap in the public imagination may be as important as any rocket, because belief in a careful, achievable path is part of how humanity finally steps onto the red planet and stays.